A compromised OpenClaw agent has full access to your host machine, file system, network, processes, everything. One bad tool call, and your production secrets end up on paste bin. 6 days ago, NVIDIA shipped the fix. Welcome to Prentice AI, I'm Daniel. We make videos that help developers and businesses deploy AI safely, and today we're doing a proper deep dive into NemoClaw's architecture. This one's for developers, DevOps engineers, anyone deploying AI agents in production or thinking about it. We're going layer by layer through the security stack, looking at real code, real configs, and I'll walk you through the full install. Chapters are timestamped below so you can jump to whatever section you need, and every repo, doc, and source we reference is linked in the description. If you spot something I got wrong or want to add context, the comments are the place. I genuinely learn from them. Alright, let's tear this apart. OpenClaw has 4,600 GitHub stars, making it the fastest growing open source project in the AI agent space, and developers absolutely love it. But here's the thing, enterprises won't go near it, and the reason is actually pretty simple. When you run OpenClaw on bare metal, the agent process inherits your user permissions, which means it can read your SSH keys, your .env files, your AWS credentials. It can curl data to literally any endpoint on the internet, and there's no audit trail, no network restrictions, no file system boundaries. Nothing. Cisco actually published a blog titled "Personal AI Agents Like OpenClaw Are a Security Nightmare," and honestly, they weren't wrong. Because for any organization handling PII, financial data, medical records, or legal documents, deploying an uncontained OpenClaw agent is just a non-starter. And Harrison Chase, the LangChain founder, whose frameworks have over 1 billion downloads, said it directly: the bottleneck has never been interest. It has been the absence of a credible security and governance layer. That's exactly what NemoClaw is. It's that missing layer. So March 16, 2026, GTC in San Jose, Jensen Huang announces NemoClaw alongside the broader OpenShell platform. And his exact words were, "OpenClaw opened the next frontier of AI to everyone." Every company in the world today needs to have an OpenClaw strategy, an agentic system strategy. This is the new computer. And then Peter Steinberger, who co-created OpenClaw, framed the collaboration like this: we're building the claws and guardrails that let anyone create powerful, secure AI assistants. Now, the launch partners tell you a lot about who's paying attention here: Box, Cisco, Atlassian, Salesforce, SAP, Adobe, CrowdStrike, ServiceNow, LangChain, Dell, HPE, CoreWeave. This is not a weekend project, this is enterprise infrastructure backed by the most credible company in AI compute. It shipped as Apache 2.0, alpha status, with a clear warning that interfaces and APIs may change without notice. But the architecture is solid, and that's really what we're here to examine. So NemoClaw is 2 components, not one binary, but 2 independently versioned artifacts, and the separation matters. The first is a TypeScript plugin that runs on your host machine. It registers under the OpenClaw.extensions namespace and gives you the CLI commands you'll actually use: NemoClaw onboard, NemoClaw connect, NemoClaw status, NemoClaw logs. Think of this as your control plane. It never touches the sandbox directly, it delegates everything to the second component. And that second component is a Python blueprint, a versioned artifact pulled from an OCI registry. This is the orchestrator, the thing that actually does the work, creating sandboxes, applying security policies, configuring inference routing, managing the whole life cycle. And it has its own release stream, completely independent of the plugin. Now, why the separation? The plugin is your stable interface. Think of it as the contract between you and NemoClaw, while the blueprint evolves rapidly underneath with new security policies, new sandbox configurations, new inference backends, all without ever breaking your CLI workflow. You update the blueprint and your commands stay exactly the same. Alright, let's walk the plugin source. This is the exact file structure you'll find. There are 2 directories under src that really matter here. The commands directory is your CLI surface, 5 commands, each in its own TypeScript file, nice clean separation. And then the blueprint directory handles the whole supply chain, resolving which blueprint version to use, fetching it from the OCI registry, verifying its digest, and executing it as a subprocess. And notice state.ts, that's the persistent state management, handling run IDs, session references, checkpoint data. This is how the plugin keeps track of what the blueprint is doing across invocations, so it doesn't lose its place. Now the blueprint itself is actually much leaner, just 3 files. Blueprint.yaml is the manifest. It declares the blueprint version, supported profiles, and compatibility constraints with the plugin. Runner.py is the actual orchestrator that implements the plan, apply, and status commands driving all OpenShell CLI interactions. And then OpenClaw sandbox.yaml is the security policy, basically the rulebook that defines what your agent can and cannot do. We're going to spend some serious time on that file in a bit. The blueprint lifecycle is a 5-stage pipeline, and understanding it is really the key to understanding how NemoClaw operates as a whole. Stage 1 is resolve. The plugin figures out which blueprint version to use, it checks your local cache, queries the OCI registry for the latest compatible version, and handles version pinning if you've specified one. Stage 2 is verify. Before anything executes, the blueprint artifact's cryptographic digest gets verified against the registry. This is your supply chain security. It guarantees that nobody has tampered with the blueprint between NVIDIA publishing it and you running it. And if the digest doesn't match, execution stops. Full stop. Nothing proceeds. Stage 3 is plan. The blueprint looks at the current state of your OpenShell environment and figures out what resources need to be created, updated, or removed. If you've used Terraform before, this is basically the same concept. It tells you what's about to happen before anything actually changes. Stage 4 is apply. This is where the plan actually gets executed. The blueprint drives all the OpenShell CLI interactions, creating the sandbox, applying network policies, configuring the inference gateway, mounting the file system with the right permissions. Everything the sandbox needs to exist happens in this stage. And stage 5 is status. This reports the current state of the blueprint run and sandbox health, and it's what NemoClaw status calls under the hood. It queries the running state and gives you a health check. Now, the really beautiful thing about this pipeline is its idempotency. You can rerun it safely at any point. If a stage has already completed successfully, it's a no-op, and if something failed partway through, it just picks up where it left off. Alright, that's the architecture. Now let's get into the part you're really here for, the security layers. Security layer 1 is network isolation. The sandbox runs inside its own Linux network namespace, which means it has a completely separate network stack from your host. The agent doesn't share your network interfaces, it has its own. The only bridge between the sandbox's network and the outside world is the OpenShell gateway, and every single outbound connection from the agent passes through it, where it gets checked against an allow list defined in YAML. The default allow list permits exactly these endpoints: integrate.api.nvidia.com for inference, github.com and api.github.com for GIT operations, clawhub.com and openclaw.re for the plugin ecosystem, registry.npmjs.org for npm packages, get-only, and api.telegram.org for messaging integration. Everything else gets blocked. And here's what makes this really powerful: the allow list is hot reloadable. You can update the network policy without restarting the sandbox, add a new endpoint, remove one, tighten restrictions, all live. And when the agent tries to reach something that's not on the list, it doesn't just silently fail. The connection gets blocked, and the operator sees a real-time approval request in the TUI with the full details, the target host, the port, and which binary initiated the connection. Layer 2 is file system isolation, and this one uses landlock LSM, that's Linux Security Module, enforced at the kernel level. So we're not talking about application-level sandboxing here. The kernel itself prevents the agent from accessing paths outside the policy. The agent gets read-write access to exactly two directories, sandbox, which is its home, and TMP for temporary storage. System paths like ERZ, lib, proc, dev urandom, app, etc., and vard log are all mounted read-only. And everything else? It's not just forbidden, it's invisible. The agent literally cannot see your home directory, other users' files, or system configuration. And this gets locked at sandbox creation and cannot be modified while the sandbox is running. Even if the agent somehow gained elevated permissions inside the container, the kernel-level landlock policy stays enforced. It's a hard boundary, not a soft one. There's no talking your way past it. Layer 3 is SecComp, Secure Computing Mode. So every interaction between a process and the Linux kernel happens through system calls, and SecComp defines a whitelist of which syscalls the agent process is actually allowed to make. The dangerous calls all get blocked at the kernel level, setuid for becoming root, trace for attaching to other processes, mount operations, raw socket creation. So even if an attacker somehow achieves code execution inside the sandbox, they still can't escalate privileges, can't attach a debugger to another process, can't mount new file systems. The kernel just refuses the call before it ever executes. And just like landlock, SecComp profiles get locked at sandbox creation and stay immutable for the entire session lifetime. Now layer 4 is inference routing, and this one works differently from the other three. It's not about containment, it's about data flow control. And honestly, this might be the most important layer for anyone in a regulated industry. All inference requests from the agent get routed through the OpenShell gateway, so the agent never connects directly to any model endpoint. The gateway intercepts every request, and this is where the privacy router sits. The default configuration routes to NVIDIA's cloud endpoint at integrate.api.nvidia.com, using NemoClaw 3 Super 120B, that's a 120 billion parameter model with 12 billion active parameters via mixture of experts, with a 131,000 token context window. So we're talking serious capability here. But here's where the privacy architecture gets really interesting. Sensitive data can be routed to a local NemoClaw instance, keeping it entirely on machine, while general queries go to the cloud for maximum capability. The gateway makes this routing decision, and you as the operator control the policy. You can even switch models at runtime without restarting the sandbox. There are 4 cloud models available: NemoClaw 3 Super 120B for production, Ultra 253B for complex reasoning, Super 49B for balanced workloads, and Nano 30B for cost efficiency. Local inference through Ollama and VLLM is experimental but functional with some community workarounds. Alright, let's look at the actual policy file, OpenClaw sandbox.yaml, because this is the single source of truth for what your sandbox can do. The line to pay attention to is on_violation, prompt_operator. What that means is blocked network requests surface to you in real time rather than silently failing. You get to decide. The agent doesn't. And this is the file you customize per deployment. Need to add a client CRM API? Put it in the egress allow list. Need write access to a shared mount? Add it to writable. The whole thing is declarative, auditable, and version controllable, exactly what you want for a security policy. The sandbox itself is a container image hosted at ghcr.io's NVIDIA OpenShell community sandboxes OpenClaw, about 2.4 GB compressed, and it runs inside K3s, which is lightweight Kubernetes, managed entirely by the OpenShell platform. Inside this container, OpenClaw runs with the NemoClaw plugin pre-installed. The agent runtime, the tool framework, the memory system, all of it lives inside the sandbox. And the agent has absolutely no awareness that it's containerized. From its perspective, sandbox is home and the network is just a bit limited. The container is ephemeral by default, which means session state persists in a sandbox across connections, but the container itself can be recreated from the image at any time. So this gives you a clean slate option. If something goes sideways, just destroy and recreate, and the blueprint's plan apply cycle handles that whole process idempotently. So what's actually running inside? You've got the OpenClaw gateway process handling message routing and session management, the agent process, PI, handling inference requests and tool execution, and then tool calls spawn subprocesses that inherit all of the sandbox's security constraints. Every subprocess is bound by the same seccomp profile, the same landlock policy, the same network namespace. There's no escape hatch. For minimum requirements, you're looking at for vCPUs, 8 gigs of RAM, Ubuntu 22.04 or later. But in practice, 16 gigs of RAM is what you really want, because the sandbox image plus Docker daemon plus K3s plus the OpenShell gateway all running at the same time can trigger the OOM killer on memory-constrained systems. So if you're running tight on RAM, make sure you configure at least 8 gigs of swap. Let me give you the inference flow in one clean diagram. The key thing here is the agent never sees the real endpoint. It makes requests to the gateway's local address, and the gateway handles all the upstream routing. Which means you can swap inference backends, cloud, local, hybrid, without changing a single thing in the agent's configuration. The agent doesn't know, and honestly, it doesn't need to know. So when the agent hits an endpoint that's not on the allow list, the OpenShell TUI surfaces it immediately. You see the target host, the port, the binary that initiated the connection, and you approve or deny. If you approve, that endpoint gets allowed for the current session only. And here's a key detail: approved endpoints don't persist across sandbox restarts. If you want permanent access, you add it to the policy YAML. This is by design. Session-scoped approvals prevent policy drift, so every permanent change is an explicit, auditable edit to the policy file. Alright, let's shift gears to the practical side, getting this thing running. Prerequisites: you need a Linux machine, Ubuntu 22.04 or later, or Windows with WSL2. For or more CPU cores, 8 gigs of RAM with 16 recommended, 20 gigs of free disk with 40 recommended. You'll also need Docker or a compatible container runtime, and heads up, Podman on macOS is explicitly not supported yet, so use Columnar or Docker Desktop instead. And finally, an NVIDIA API key from build.nvidia.com. Installation is literally a single curl. This downloads and runs the installer script, which pulls the NemoClaw CLI, resolves the latest blueprint from the OCI registry, verifies its digest, and sets up the OpenShell environment. On a reasonable connection, expect 3 to 5 minutes, and most of that time is just pulling the 2.4 gig container image. This is where the full blueprint lifecycle kicks in. Under the hood, Resolve finds the latest compatible blueprint, Verify checks the digest, Plan figures out what OpenShell resources to create, the sandbox definition, network policies, inference gateway configuration, and then Apply executes the plan, pulling the container image and standing up the sandbox. The guided wizard walks you through your NVIDIA API key and your assistant's name. When it finishes, you've got a running sandbox with all 4 security layers active and ready to go. This drops you into an interactive shell inside the sandbox, so now you're seeing the world exactly the way the agent sees it: restricted file system, namespace network, filtered syscalls. Try to read etc. shadow, permission denied. Try to curl an endpoint that's not on the allow list, connection blocked. It's a good way to really feel what the security layers are doing. For debugging, you've got status gives you the blueprint's current run state plus the sandbox health check, and log streams real-time output from both the blueprint orchestrator and the sandbox itself, which is essential when you're trying to figure out why a tool call failed or why a network request got blocked. As for common issues, if onboard fails with memory errors, you need more RAM or swap. If connect hangs, check that Docker is running and the container image actually pulled successfully. And the plugin commands under OpenClaw and NemoClaw are still under active development, so you'll want to use the NemoClaw host CLI directly for now. Now let's be real about what this is. Alpha means alpha, and there are some genuine rough edges you should know about. The OpenClaw NemoClaw plugin commands, the ones that run inside OpenClaw's own CLI, are incomplete right now, so use the host NemoClaw CLI as your primary interface. Local inference through Ollama and VLLM is still experimental. Community members have actually gotten VLLM working via Iptable's hacks in WSL2, which is creative, but those rules don't persist across reboots, so you'll need to reapply them each time. Nematron models use a tool call text format that isn't OpenAI compatible, which means if you're doing local inference, you may need a custom gateway to rewrite tool calls in the SSE stream. Session-approved network endpoints don't persist either. Every sandbox restart means reapproving, or you add them to the static policy. macOS with Podman, still not supported. Use Columnar or Docker Desktop. And documentation is sparse, honestly. The README is your best friend, and the GitHub issues are your second best. So what's coming? Based on the architecture and partner announcements, stable Ollama and VLLM local inference support is clearly a near-term priority, along with persistent session-approved endpoints, more complete plugin commands inside OpenClaw, and NIM, that's NVIDIA Inference Microservice, integration for production-grade local inference. Looking further out, there's the box integration for document lifecycle management that was announced at GTC, Cisco AI Defense integration for enterprise threat detection, skill packs for Salesforce, SAP, and ServiceNow, and the Nematron for family being co-developed with Mistral AI, purpose-built for agentic workloads. NemoClaw is Apache 2.0, and the repo is at github.com/NVIDIA NemoClaw. File issues, especially around platform-specific bugs, WSL2 edge cases, and local inference workflows. And the community Discord at discord.gg/xfpfpv9uvx is active and genuinely responsive. So to bring it all together, NemoClaw solves the exact problem that's been keeping OpenClaw out of production environments. You've got for kernel-level security layers, declarative policy management, supply chain verified blueprints, and an inference routing architecture that gives operators real control over where their data flows. It's alpha, and it absolutely has rough edges. But the architecture is sound, the backing is serious, and the window for learning this stack is right now, before everyone else catches up. So here's what I want from you: if you've actually tried deploying NemoClaw, or if you've run into the security problems it's trying to solve, tell me about it in the comments. What's your setup? What broke? What worked? That kind of real-world feedback is genuinely more useful than anything I can find in docs. Next episode, we're building a full NemoClaw deployment for a regulated industry, real data flows, real policy configs, real compliance requirements. Not theory, actual deployment. Subscribe if you want to catch that one. Every link, repo, and source from this video is in the description. Thanks for watching. Seriously, I appreciate the time. Until next time, read the source, break the sandbox, file the issues. That's how alpha software gets to V1. *End of script.